Hi and welcome to Physics Hi, and today is the first in a series of videos that I'm going to do where I go through answers of various HSC style questions, both multiple choice and short answers. But in particular, I'm going to divide them into the 4 modules so that if you're doing the HSC exams, you can prepare by concentrating on each of module 5 through to 8. Now, if you are not an HSC student in New South Wales, this still can be very helpful for you because in today's topic, I'll be looking at advanced mechanics, which deals basically with projectile motion, gravitation and circular motion. And if you're studying that, this is helpful as well. Now, in all of these videos that I'm going to produce here, the important thing here is just to attempt the questions beforehand so that you go through the answers having tried the questions yourself. Now you can do that one of 2 ways. You can pause the video and then try the question and then look at the answer. Or secondly, I'll be posting on my website the questions themselves, and I'll put a link in the description below so that you can try them beforehand before watching this video. So today we're going to concentrate on advanced mechanics from the exams of 2009 and 2010. Now before we start, I really value your support, so maybe buy me a coffee. The link is in the description below. So let's get going. So our first question says this: a fast moving space probe passes close to a planet, and during its journey, how does the gravitational field affect the speed and the direction of the probe around that planet? And we have these 4 options. Now let's quickly review what happens as a satellite goes around a planet. So here's my planet, and we have a satellite coming across, and it will go around like so. Now what happens? Well, of course, it's in a gravitational field, so it experiences a force, and so the gravitational energy of the satellite is going to change, and subsequently conservation of energy means also the kinetic energy is going to change as well. Now it's clearly closer here than, let's say, over there. Okay, obviously it should be a nice perpendicular line, but the point here is the gravitational energy gets less, which means the kinetic energy increases, and thereby the magnitude of the speed is going to increase. Now, in terms of the path, it goes around in a curve, so its direction is changing as well. So therefore the speed changes as well as the direction as well. So therefore our only option really is C. Our next question has a satellite moving in a circular orbit at a radius of around 7 million meters. I say around because it's rounded to 2 significant digits. If the speed of the satellite is 8.1 by 10 to the power of 3 meters per second, what is its centripetal acceleration? Well, of course, the centripetal acceleration is simply determined by simply v squared over r. Now, if we substitute the values in, we get 8.1 by 10 to the power of 3, and we of course square that, and we divide this by the radius, which is 7.0 by 10 to the power of 6, and you're going to get a value in the order of 9.4 meters per second squared. It's a little less than that, but because the values we're given is in 2 significant digits, then it's appropriate to provide the answer that is also in 2 significant digits. We now have a satellite moving from a geostationary orbit to a higher orbit. Now, what statement of this orbit is correct? Now, as I go through these questions, I am also going to quickly give a sort of a review. What is a geostationary or a geosynchronous orbit? Well, it's a satellite that basically has a period of 24 hours. Now, as long as the orbit is in the plane of the equator and it is far enough so that the period is 24 hours, it will remain stationary relative to a position left on Earth. So let's draw that around here. This is not to scale. We've got a circle. In fact, got a very, very poor circle, but you get my point. Now, what is happening here? It's moving to a higher orbit, and so it's now moving further away, and I'll just draw to there. And so here's my satellite in position A, and there's my satellite in position B, and we're asked, well, how does it get there? Well, let's go through it. It's increasing its gravitational energy. It's also increasing the total energy. All right, so in other words, the kinetic energy changes, the gravitational energy changes, but the total energy also increases as well. And so therefore work has to be done on the satellite to move it from point A to B due to conservation of energy. So the difference between the two positions, that is, the differences between the total energies, therefore will contribute to the work done. So we've got what? During the move, the gravitational potential energy decreases. Well, I've just said that's not true. It actually gets stronger because at a point of infinity, it's 0. These are all negative values, and so therefore it actually has a larger value at B. So therefore A is incorrect. If we go to B, the change in gravitational potential energy is independent of the mass. Well, the gravitational energy is equal to negative G mm over r. Both masses are there, both the satellite and the mass of the Earth, so therefore B is incorrect. Now let's look at C. The work done is the difference between the gravitational potential energy of the higher orbit and to that of the geostationary orbit. That's not quite correct because we also have a change in kinetic energy, which I've already stated, and so therefore as a result that's not correct. It's the total energy, that difference, that determines the work done on the satellite. So D, the work done is the energy required to move the satellite, which is in a gravitational field, from a very large distance away to the higher orbit. That is actually the correct answer. Now, why is it the correct answer? Because that is actually the definition of determining the gravitational energy. It is the work done moving from a point of infinity to that position of whatever you move it to. And in this case, this is the work done, and therefore that's the correct answer. Let's look at number 4. Now we jump into a projectile motion question. And of course, projectile motion follows the Galilean analysis that the horizontal motion is constant velocity, the vertical motion is accelerated at a constant rate, resulting in a parabola. Now that's a simplistic model, of course. We are ignoring the fact that air resistance actually plays a part. We're also ignoring the fact that the surface here is seen as flat, when in reality, of course, it's curved. We're standing on a curved surface, the Earth. But it's a very, very good approximation to use a parabola for our analysis. Now, what does that mean? That basically means no matter what horizontal velocity we fire it at, whether it's Vy or, of course, Vx, they all have the same acceleration. And therefore, if they have the same acceleration and the same displacement, that also means the time that they take will be exactly the same. So with that in mind, you can straight away see that A and B are incorrect because they have them falling at different rates or different times, and we've just established they're actually the same. Now, they hit the ground simultaneously, but the answer is not C. The same velocity vertically, yes, that's true, but they have different horizontal velocities. So the combined velocities, both the horizontal and the vertical, will mean that the velocity of y overall will be higher, and so therefore D is our correct answer. Question number 5. During a lunar eclipse, the Earth moves between the Sun and the Moon, and what happens to the force exerted by the Sun onto the Moon? Well, of course, the force that is existing between the Sun and the Moon is simply due to the formula of Fg mm over r squared. Now, whether another object goes in between them doesn't matter. Therefore, the force between the Sun and the Moon and the Sun, because of course Newton's third law is that the force that the Sun exerts on the Moon is the same as the force that the Moon exerts on the Sun, is not affected by the presence of the Earth. And so as a result, the only possible answer, it remains unchanged. 2010. We're dealing here with another question 1, and generally speaking, the easier questions are earlier. We have the International Space Station orbits the Earth at an altitude of approximately 330 kilometers. We consider that a LEO, a low Earth orbit. Now we have another satellite, the Meteosat, which is in a geostationary orbit, so we call it a GEO, a geosynchronous or geostationary orbit of 36,000 kilometers. Now, which of the following compares the orbital velocity and the orbital period? Well, let's quickly review our mathematics and then we'll use that to analyze the question. First of all, the orbital velocity is equal to the square root of G capital M over R. So you can see now there's an inverse relationship. The further a satellite is, the lower the orbital velocity. The other formula we need to consider is Kepler's third law, which says that the ratio of the radius cubed over t squared is a constant value, and of course Newton analysed that to be equal to gm over 4 pi squared, which also means all of these things are the same value, a constant, where m is the central mass. Again, what this is saying, if r is bigger, then the period gets bigger. So in essence, what we're saying is, if we're interested in the orbital velocity and orbital period of these satellites, the International Space Station, being closer, will have a higher velocity and also a shorter period. And if you look at the options, we have a greater velocity here and a greater velocity here, right, for the International Space Station. Now, what about the Meteor? Now, this is, remember, this is the geostationary satellite, so its orbital period will be longer. And so we have a longer orbital period for that guy and a longer for that answer, but you can see the only possible answer will be C. Now, question number 2. Which of the following best describes Galileo's analysis of projectile motion? Again, I stated that earlier. Galileo basically said that the two are independent, and therefore that results in a parabola. A projectile launched with a great enough velocity would escape Earth's gravity. No, that's what Newton said, so A is incorrect. B, a projectile would travel in a straight line until it ran out of momentum, and then it would fall. That was a misconception that actually Galileo tried to suggest was incorrect. So although it relates to Galileo, it's not what Galileo did. C, a projectile launched from the equator towards the east will have a great enough velocity, it would orbit Earth. Again, this is about Newton, so it is incorrect. And finally, the projectile would travel in a parabolic path. Well, from there on in, we can see that is the correct answer, so D is our correct answer. Next question. Now, this is a little bit more tricky because here we've got some graphical analysis, and generally speaking, when we look at graphical analysis type questions, we're looking at higher order interpreting information that are in different forms, and in this case in a graph. And this is what we would expect in the New South Wales context, a band 5 type criteria. So we would expect students who are not capable of band 5 or band 6, so band 4 may struggle with this question, but these are sorts of the questions that would differentiate for the bands 5 and band 6. Now we're told here that this ball is launched at 45 degrees, and that means, of course, that if we to draw this as a parabola and as it's drawn, then here it's at 45 degrees. Clearly it has a velocity that is only the horizontal component. And of course down here we have a velocity that is both that horizontal component, which of course is constant throughout its journey, and of course we have a vertical component at these points, but no vertical points over here. And then obviously the changes. So in other words, the velocity is a maximum at the beginning and at the end, and a minimum, but not zero, at the top of the trajectory. Now with that in mind, since the velocity squared is proportional to the kinetic energies, which is what we're interested in, therefore the lesser the velocity, the lesser the kinetic energy. And so therefore we can automatically rule out a possible answers. So therefore A is incorrect because we're actually saying that the kinetic energy gets less as it goes up. So A is out. Now, the next one we want to discount is the fact that the velocity is never equal to zero. Therefore, the kinetic energy never equals to zero. So at no point can you have kinetic energy equaling zero. That discounts D and discounts C because we have them at zero at two particular points in time. And that finally gives us the answer of B. Now, some of you may look at D, and that's the discriminator. We have this straight line, which is actually the graph if I were to make this the velocity. But because the velocity actually never equals zero, this only applies really to the vertical component of velocity, it can't be correct. And besides, the velocity gives us a linear relationship, but it's a square relationship for kinetic energy, so we have to get our parabola back again. So here's the parabola, B is the correct answer. Question 5, now we're dealing with circular motion, and we have a mass that is swung around a horizontal circle, and it completes 5 revolutions in 3 seconds, and the circle has a 2-meter diameter, and we're asked which of the following forces is closest to that required to keep the mass moving at this circle. What is this question all about? its centripetal force. So the centripetal force is equal to mv squared over r. Now before we go on, of course, we need to work out the velocity. It completes 5 revolutions in 3 seconds. That in essence means we have the period equaling basically the 3 seconds divided by the 5. In other words, its period is 0.6 seconds. That allows us to do 5 of them in 3 seconds. The velocity is of course equal to 2 pi r, or in our case pi d, because we're given the diameter, divided by the period, which we know is already 0.6. So now we have a velocity, and that's equal to pi times d. Now the d is 2 meters, so what we have is 2 pi over 0.6, and that gives us 10.47. Now we have the mass, that is equal to 0.2. We multiplied by our value that we established was 10.47, and we square that and we divide that by the radius, and our radius in this case is 1 meter, and we get 21.9 newtons. Looking at our responses, it's closest to the 20 newtons, so D is our correct answer. Now in this question, it's not about content, it's about, do you understand the relationships that we have between variables and how they are shown in graphs. Now in this case, we have 4 graphs, and they're all linear graphs, and they all show different relationships, and we're interested in the relationship between the terminal velocity and the radius, but we're told that the terminal velocity is proportional to the square root of r. Now they can also be written like this: vt all squared is proportional to r. That means if I graph vt versus r, I actually get a parabola, but it's a side-on parabola. Now, in our case, we have all linear graphs. So what's happening here? They're linearizing the data. And by that, what they're doing is they're graphing the relationship. So for example, we have r as our independent variable. It's going to be on the x-axis. In order to get a linear relationship, we have to graph vt squared, which is going to be on our y-axis. And so therefore, our B is the correct relationship. A is not correct because that shows a direct relationship between V and R. C shows the relationship, but in this case, it's V is proportional to R squared, not the square root of R. And of course, in D, we've got the square root of V, which is not correct either. Now going to a longer response question. And we have an astronaut throws a stone on the top of a cliff on the moon. The stone hits the ground below 21 seconds later, and the acceleration due to gravity on the moon is 1.6 meters per second squared. Now this is a simple projectile motion type of problem. The only difference is we are using the acceleration of 1.6, not 9.8 meters per second squared. And we're asked 3 things. The first is to calculate the horizontal component of the initial velocity, show you working. B, the vertical component of the stone's initial velocity, show you working. And C, on the diagram, sketch the path the stone would fall if the acceleration due to gravity was higher. The initial velocity is the same. Now, notice here, it says twice, show your working. And my big advice to you is when you do your questions in the HSC, you don't just write down the answers, actually set out your problem so that if you do get the wrong answer at the end, you'll probably get some marks to show good process, because that's what we're trying to do. We're trying to show or see whether students understand the correct process. So you might not get the right answer, but you actually may show good process, which means you get the mark. Now let's go through it. It says calculate the horizontal component of the stone's initial velocity. Now we're told, and I always tell my students, what we do is we go V, U, A, S, T, and some of you do SUVAD, that works too, S, V and T for the horizontal component. And I always do this just as an automatic response to projectile motion questions. What we do is write down all the variables that we have. Now we know that the time is 21 seconds, so we can put that in. We know the vertical displacement is negative 150 meters. You can see it's vertical. We know the acceleration is negative 1.6 meters per second squared. The initial velocity, of course, is what we're interested in. And of course, we're only interested in the y component here. we have Vx, and our displacement horizontally is 300 meters, and our time is exactly the same, it's 21 seconds. To work out the horizontal component of the velocity, well, we know that the velocity in the horizontal is simply displacement over time. So we have s over t, and so therefore you get 300 over 21, and you get 14.3 meters per second. So we've just calculated the horizontal component. So now let's have a look at the vertical component. As you can see, we have u, a, s, and t. So the formula we need is s is equal to ut plus a half a t squared. The first thing you might want to do is rearrange it, but can I advise you not to rearrange it until after you substitute it in. You're less likely to make mistakes. Also, you're more likely to get part marks because you have substituted into a correct equation. And so what we do is write everything down. So u is going to be equal to negative 150 plus 352.8 all over 21, which is going to give you a value of 9.6 meters per second. So there are our two values. Finally, it says on the diagram, sketch the path that the stone would follow if the acceleration due to gravity was higher. Well, there are two things that are going to change. We're going to have a shorter range. So we're going to basically land a shorter path. But it's also not going to get as high. And so therefore we would expect that the vertical height, maximum wise, may be lower. And so that will give us a path that looks something like this. And therefore you get 2 marks because you showed that the vertical height is lower and also the range is shorter. And that was 2009 to 2010. Now, please remember, like, share and subscribe. Put a comment down below if this has been helpful for you. And as I said earlier, if you have the opportunity to support me by buying me a coffee, click the link in the description below. In any case, my name is Paul from Physics High. Take care and bye for now.